Welcome back, and today we are going to really get our hands dirty computing some examples of semi-direct products. Now that we know what these are. I already talked about an example from last time, but we're going to get more into the weeds now. So thinking like a mathematician, of course, we should always try and find the simplest example first, and then expand out from there. So what is the possible simplest example we could take for the normal subgroup in a semi-direct product, or for either factor for that matter? Well, it would be the trivial group, but hopefully it's not too hard for you to convince yourself that taking this as either factor simply leads to the original group. Not a very interesting result. Okay, the other thing that we talked about is, thinking about the normal factor now, the other possibility is that z mod 2 is the normal factor. But again, essentially because its automorphism group is trivial, the only possibility in this case is if z mod 2 is just a factor of a direct product. Not very interesting. We could then, so just going up to the next level of simplicity, we try to consider a group of order 3. There's only one up to isomorphism. So z mod 3, semi-direct product. Now again, let's try and take the simplest non-trivial example for the other group. That could be the integers mod 2. But I've already told you, so mind you, of course, this depends on a choice of homomorphism from phi, the integers mod 2, into the automorphisms of z mod 3. But there's only two of these, so either it would get sent to 0, or either it's the zeromorphism or the identity morphism. And I already gave away the answer of what it should be, but let's think about this in general. Right, so I mentioned previously that this should be this should give us the dihedral group. Very natural to ask, well, does that phenomenon generalize? So if we think about it for a moment, if you remember your dihedral group of order n, it can be written in terms it's generated by your r is just some choice of rotation, and s is some choice of reflection. And we know that we have the relations, of course, n rotations is the identity. You do a reflection twice, it's the identity. And if you conjugate a rotation by a reflection, then you get the inverse rotation, right? So this totally determines the dihedral group. So how might we try and figure out if this is a semi-direct product? Well, we go looking for a normal subgroup. And so we can see, of course, if you conjugate a rotation, by a rotation, you still have a rotation. And this tells you that if you conjugate by a reflection, you still land in rotation. In other words, we know that the group of rotations is a normal subgroup of the dihedral group. And of course it is isomorphic to z mod n, so that is a natural candidate for our normal subgroup. And then we have this order 2 thing left over being the reflection, right? So a natural guess would be that we have the dihedral group is isomorphic to a semi-direct product of this form. The only question is, what do we take for that homomorphism phi? And really the hint is right here, right? Because if we think about our form of the semi-direct product, we're sort of thinking about it as like pairs R and S. And we need to think about how the S would act on such an R. And here we do have this sort of conjugation action. In fact, we can generalize this operation so that if we had S R to the I, S inverse, well, we could peel off one of the r's, right? So this would be s, r, r, let's say I minus 1, s inverse, but this is s, r, s inverse s, r, I minus 1, s inverse. And then using that relation, we know that this becomes R minus S R I inverse S inverse. And now we simply repeat the argument inductively until we end up with R minus I. Okay. So that gives us a bit of a hint. So if we're thinking about, the isomorphism from here as sending, say, R to the I to I, this tells us that our choice of homomorphism from Z2 into the automorphism group of Z mod N should be the following. So, of course, at the identity, it has to be the identity. But at 1, at the non-trivial element, applied to any m, we'll send it to its minus, to its negative. And so you can check, indeed, this does define a automorphism of the integers Z mod N. So okay, now that we have that, let's try and prove that this is indeed defines a semi-direct product structure. So that is, it's isomorphic to a semi-direct product. So my isomorphism from Z mod N, semi-direct, Z mod 2, in this case, into the dihedral group, 2.n, is going to be given in the following fashion. So I'll write square brackets for the semi-direct product in this case, just because things will get messy, especially in a theorem afterwards that I'm going to prove. So in order to show that this is a surjection, so we know that the order of this group is 2 times n, and the order of this group is 2 times n. So if we can just show, for example, that it's a surjection, it must be a bijection. So in order to show that, first note that if I had some, so I've sort of given the generator and relation presentation up here. So everything is just some word in powers of R and powers of S. So let's suppose first that I had, let's say, 2 S's on the left, and then ABC are just some combination of R's and S's. And then it goes on. Well, those S's cancel out, and this would be left with, this would just be ABC ... If I had 1 S and then some power of R and then some other combination of letters, well, this would be S R to the I, S inverse S, right? Our favorite mathematician's trick of just adding 0 or multiplying by 1. And then now we know that this term from our relations is just R minus I. And I still have this S here and then ABC ... So the point is I can always cook it up so that I've got just powers of R on the left. By the same token, suppose that I had ... ABC, I had S and then some power of R. What could I do? Well, I will do exactly just the same trick. So I've got ABC, SRI, and I can write S inverse S. So then that conjugates to ... ABC R minus I, and I just have this S over here. So what's the point of this calculation? Well, it says I can always shuffle all of my R's to the left, and I can always shuffle all of my S's to the right. So in other words, every element of D2n can be written in this form, R to the power I times S to the power J. And so certainly this map is surjective, right? Because I just have J being 0 or 1, and yep, that's taken care of this factor. And then I goes from 0 up to n minus 1, which of course is taken care of by the second factor. Great, so I know I have a bijection. Why is this a homomorphism of groups? Well, we're just going to have to go through the computation. So, and this will be a great warm-up for the next computation. So, well, there's really 2 cases. So I have psi of I0 and jk. And what happens in this case? Well, the multiplication, if I multiply these two terms together, the multiplication is I plus phi at 0 applied to j, 0 plus k. And this is going to be psi of, well, this is I plus, this is phi at 0, so it's the identity, so it's I plus j, k. Where does this get sent to? Well, this is simply, by definition, r to the I plus j, s to the k. And, well, I can move this over so it's r I, r j, s k. And I mean, s to the 0 is just the identity, right? So this is the same as ri s0, rj, sk. But wouldn't you know it, this is, in fact, psi of I0 times psi of jk. Okay, the one other case, right? This is pretty general. This is for any I, j, and k. The only other case is when the 0 is a 1. So let's do that case. So we have psi I1 jk. This is going to now be psi of I plus phi 1 acting on j, 1 plus k. And so in this case, remember, this is the automorphism that sends j to minus j. So I have psi of I minus j, 1 plus k, which we defined to be r to the I minus j, s to the 1 plus k. But of course, I have, so ri, r minus j, s, sk. And again, the mathematician's favorite trick, I can put, so here I'll put s inverse, here I'll put s, r minus j, and now this s, I can actually write s as its own inverse. So I'll write this as s inverse, s to the k. But this term now is rj, and s to the minus 1 is, again, just equal to s. And sure enough, this is exactly what we wanted. This is ri1 times psi of jk. So that verifies it's a homomorphism, and therefore we've just seen all of the dihedral groups can actually be written as this special kind of semi-direct product. Okay, what are all the semi-direct products then? Sort of going through the list, we might think, okay, let's look at all the small examples. So, groups of order 0, that's totally trivial. We know there's only one group of each prime order, so 2 and 3, nothing there to think about. 4, well, we already know, what the groups of order 4 are. But again, a group of order 4, to be a non-trivial semi-direct product, you would have to have a z mod 2 as your normal factor, and we already saw that just results in the direct product. So I guess the takeaway, interestingly, is that what does that tell us? That tells us that z mod 4 actually is not a semi-direct product. So not every group can be written as a semi-direct product. There's something else going on there. I want to show you one more interesting example. So 5, again, prime order. 6, we see there's only one choice of non-trivial semi-direct product, which we just encountered. 7 is prime. 8, here things get interesting again. So let's consider what are the possibilities for our normal subgroup. Again, it can't be z mod 2 because that just leads to something trivial. So it can't be 2. The orders could only be 2 or 4. If it were z mod 4 being the trivial, being the semi-direct product, then what could we say? Well, in this case, the automorphism group of Z mod 4 is isomorphic to the integers mod 2. So again, our choice of homomorphism from Z mod 2 into the integers mod 2, we have the zero homomorphism, which would give us a product, just a direct product. And then we just saw that every dihedral group is a non-trivial semi-direct product of this form, so that would have to be the one other group. Now, those of you who are keen, who might know, or just are always thinking about your favorite group of order 4, what does that mean? Well, let's think about the quaternion group, right? We might think, okay, that's the one thing that we're missing in this whole discussion. So surely the quaternion group should therefore be what's our only other choice of semi-direct product we haven't considered yet? Well, the Klein 4 group, right? We take Z mod 2 cross Z mod 2 as our normal subgroup. Surely this must be the case. Well, let's think about how we could construct it, right? We need to have a homomorphism from Z mod 2 into the automorphism group of the Klein group. So Z mod 2 cross Z mod 2. This is isomorphic to 2 by 2 matrices over Z mod 2 viewed as a ring. Or, I mean, just by counting those things, we find it's a group of order 6, which is definitely not abelian, so it's isomorphic to S3. And now also recall that homomorphisms have to, the order of the image has to, of course, divide the order here. So for the trivial, for the non-trivial element, well, either this gets sent to an element of order 0, which is the identity, that is the 0 map, or this element has order 2. So in other words, our choice of our homomorphisms between the integers mod 2 and S3, this is in bijection with just all of the elements of order 2 of S3. But if you remember some of your combinatorics of S3, the only elements that we have of this form are these 3. Okay, so it seems, a priori, there's actually 3 choices of semi-direct product that we could possibly take with the Klein 4 group being as the normal subgroup and the integers mod 2. However, if we think about our Klein 4 group, okay, so just like last time when we constructed this isomorphism with the dihedral groups, we found a normal subgroup and we sort of launched off of that and the relations we know for the dihedral group to build it. So let's go looking for a normal subgroup of the quaternion group, which is isomorphic to the Klein 4 group. Suddenly we have a problem, right? Because if your group contains I or minus I, well, that automatically generates a cyclic subgroup of order 4. So it can't possibly be a group of this form. What other possibilities are there for a subgroup? Well, if you don't have I or minus I, or exact same argument for J or minus J, K or minus K, the only other possibilities is just the group plus or minus 1, the subgroup plus or minus 1, but of course that just has order 2. So actually there is no Klein 4 subgroup, so mysteriously, though we might have expected the quaternions to be a semi-direct product in this case, they are most certainly not. So if we go back to this language of exact sequences, we now have these 2 examples of a short exact sequence which does not correspond to a semi-direct product. And, well, we would love to develop a language that would allow us to talk about this. So that is where we will be going in the future. One last comment though, so we realized, perhaps surprisingly, we looked at this example, well, we saw, okay, semi-direct products of this form seem to be in bijection with the elements of order 2 of the symmetric group on 3 elements. So what are these groups? Well, they would have to be if we're already relying on the classification of groups of order 8. Well, okay, we haven't dug into the computation quite yet, but as you might imagine, they're going to be non-abelian for the exact same reason. So maybe I'll leave that to you as homework. But we have to pick one of these to correspond to a non-trivial homomorphism. In the same way, in the previous episode, we showed that some semi-direct product was non-abelian. You can argue it in this way. So we have a non-abelian group of order 8. It can't possibly be the quaternions. It must be the dihedral group. So we see that we can actually, for distinct homomorphisms, we can get isomorphic groups. And so the question is, what is the full extent to which that is the case? And so I'm going to leave you with a final theorem that classifies all of these. So to be fully general, we can consider groups up to isomorphism. So let's suppose we have an isomorphism between two groups n, which will be the normal subgroups, and an isomorphism between the two groups, which will be the quotients. And I've got some semi-direct product, right, with respect to some, so n1, q1, phi, where of course phi is a map from q1 into the automorphism group of n1. So how could I build some sort of related structure? How could I go from this to getting a semi-direct product of n1 and q2? Well, of course, I have the map from q2 to q1 given by G inverse. And how could I build a map from the automorphism group of n2? Well, if we think about, so I want to construct, let's say I have some automorphism of n1, call it H. How could I turn this into an automorphism of n2? Well, I can go backwards from n2 to n1 by taking F inverse, apply the automorphism F, and then go from n1 to n2 via F. So in other words, it's essentially conjugation by F. So that's what I'm going to mean by F tilde. And now the claim is that this semi-direct product, defined by some phi, will be isomorphic to the semi-direct product of n2 and q, defined by F tilde, composed with phi, composed with G inverse of q2. Okay, so this is the claim. Well, specifically, what should that automorphism be? So I'm going to call it psi. And it should take a pair n and q. Well, there's just sort of one obvious choice, right? How do I get an element n1 over to n2? Well, I've got this map. F that relates them. So my guess is just going to be apply F to n and apply G to q. And let's hope that everything works out. Surprise, it will. Okay. So I will maybe leave it as an exercise for you, again, to show that this is a surjection. And we already know, I mean, if F is an isomorphism and G is an isomorphism, then N1 and N2 have the same order, Q1 and Q2 have the same order. So the semi-direct product, N1 direct product Q1, that has the same order as the second semi-direct product. So again, we just need to show that the map is surjective. Well, F and G are both themselves surjective, and so it follows essentially immediately from that. The fun part is showing that we have a homomorphism. So psi of MP times NQ, maybe psi of all of this, is going to be psi of M times, oh, you know what? I wanted to start on the other end. So I'm going to start on the other end of this. It'll be psi of MP times psi NQ. So this is f of m, g of p, times f of n, g of q. So the product, remember this is the product happening over with this wonky choice of homomorphism here. So the product is going to be f of m, then phi tilde, composed with psi, composed with G inverse, applied to GP, and then that whole thing is a automorphism of N2. So then we can plug f of n into there, and we get GP times GQ over here. Okay, so we're going to look at this wacky part in the middle. So f tilde composed with psi, composed with G inverse, sub GP. This really means, applied to G, applied to P. So in other words, this is f tilde, applied to f at P. F at P is an automorphism of N1, right? So that is, if I scroll back up to a little diagram, that's like this H here. And so it makes sense to write this as f composed with phi p being an automorphism composed with f inverse. And we can even write this as phi lower p to help not get confused. And we're going to need to write it like that in just a moment anyways. So if we take that whole thing, right, and now plug in fn to this, what we get is phi composed, f composed with phi p, composed with f inverse, evaluated at fn, which is phi of fp evaluated at n. Therefore, don't need that. Therefore, this whole entire expression we have above now becomes fm times f of fp evaluated at n times gp gq. But f and g are group homomorphisms, and so this is fm times phi p n and g of p times q. But wouldn't you know it, this is exactly psi applied to m, phi p n, and pq. But finally, this is psi of m p times n q, where remember this internal thing, this is happening with respect, this is n1 semi-direct product q with respect to phi. So that is exactly this product here. And that verifies that psi is a homomorphism. So this shows us a very special case, right? How does this relate to this example? Well, if you remember your combinatorics of the symmetric group, all three of these elements are conjugate to each other. So the semi-direct products have to all be the same by simply precomposing with the an inner automorphism mapping between each of these elements. Okay, so that finishes our sort of classification of the different semi-direct products. Now we're still left with the mystery of how we're going to discuss these seemingly more complicated extensions of groups, and we'll do that in the future.